Welcome to those of you who are in the room here, and welcome to those of you who are online on Zoom. I'm Brad Jolliffe, Director of the McDonnell Center for Space Sciences, and I'd like to welcome you all to our Distinguished Lecture Series, the Robert M. Walker Distinguished. We welcome Professor Kevin McKeegan, who comes to us from UCLA, where he's the Distinguished Professor of Earth, Planets, Planetary Science, and Space Science. Covers it all. He got his bachelor's degree from St. Lawrence University before coming to, wait for it, Washington University for the PhD. He came in 1981 and studied with Robert M. Walker himself and Ernst K. Zinner, who many of you will remember. While he was here, he worked on the measurement of isotopic anomalies in cosmic dust. Very interesting start to what has become a very distinguished career. Now that he's gone, he went on from Washington University to Lawrence Livermore for a postdoc, and then shortly thereafter ended up at UCLA, where he is still today. And he has made it his business to study practically every type of solar system material he can get his hands on. And in addition to doing that, it's noteworthy that he also takes the time and the effort to try to improve the analytical techniques all the time so that we can get the most possible out of these small and very interesting extraterrestrial samples. So I wanted to mention, didn't want to forget this, there's an asteroid named after him. And he has been a participant on several extraordinary NASA missions, Genesis and Stardust, which have retrieved materials from both cometary materials and then materials from the sun itself to analyze them. And so he brings it full circle, because this is the endeavor that Robert M. Walker himself began when he came here many years ago to Washington University to use isotopic analyses to study materials not only of the solar system, but of the cosmos. And Kevin has certainly kept up that work beautifully. So it's a great pleasure and honor for me to introduce Kevin as the Robert M. Walker Distinguished Lecturer for 2021. Kevin.
All right. Well, thank you, Brad, for that very kind introduction. And thank you, all of you, for coming out tonight. And to all those people who are tuned in online, also thank you for tuning in. And I think it's possible, I don't know how many people are there, but I think it's entirely possible that my 5-year-old granddaughter is one of them. And so if you'll indulge me for a moment. Hi, Cassidy. So what I'd like to do tonight is I'm going to start off with an assertion. And I don't think, given this audience, I have to work very hard to convince you of this at all. But what I'd like to try to do is to maybe give you a slightly different perspective on this. All right, and we'll see how that develops. And the assertion is a simple one. Simple if my slides advance. Okay. There it is. Okay, so we live in a golden age of space exploration. So as I said, it's not a shocking assertion for this audience. I'm sure most of you agree, and in fact, most of the public will certainly agree with this, which is a great thing. And most people, when they think about this, will think about images such as this Hubble image, a fantastic image, you know, and other such similar images, from whether they're from ground-based or space-based telescopes, which just, you know, reveal the large-scale structure of the universe, evolution of galaxies, the beginning of our world, and all sorts of stuff. The birth and death of stars is another fantastic thing, and people will realize that there's this, you know, wonderful era that we live in, where we're discovering all these fantastic things that we didn't know about even you know, few decades in the past. Other people, maybe of a certain age, when you talk about the golden era of space exploration, And I'm certainly one of them because it turns out I'm exactly as old as NASA, born in the same month. We'll think about images like this as an exploration. And this is, of course, the famous Earthrise image from Apollo 8. And 7 months later, here we were on the moon. I love this picture because this is actually, this was taken before the invention of the selfie, but nevertheless, here is Neil Armstrong reflected in the visor of Buzz Aldrin. So it's a kind of a selfie from the Sea of Tranquility, July 1969. Are we? Get rid of the lower, okay. If I move the cursor off screen. Okay. I can't see the cursor anymore. It's a,
Options in the far
okay. There we go. I didn't, it's funny. I don't see it on my screen, so it's only over here. Yeah, I see that, but the view options is not. Oh, I see. It's up there. I have to. Okay. This will show how coordinated I am because it keeps disappearing. Sorry about that. I thought we had this. You know what? I don't want to leave. That's for sure. I'm sorry. Let me see if it roll. Oh, here it is. 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 Help me out, everyone, because it's hard. It's not. It's not.
Oh, the click doesn't do it.
I'm clicking, believe me. I've clicked 10 times. All right, so I don't know. So maybe this would not be a good thing to say leave, right? We don't want to do that. That's scary. All right, so I'm sorry, you get some extra screen stuff. Thank you. Thank you, Zoom. So how long does this pandemic have to go before we really understand how to use Zoom? I'm not sure. That was a rhetorical question. Okay, well, soon after this kind of thing, of course, right, then, well, depending on your point of view, it's a good thing or a bad thing, but, soon afterwards, people were replaced by robots, right? So it's been 50 years since we've seen anybody leave low Earth orbit. And, now we have lots of robots exploring the solar system. And now I need to get my cursor back here so that the slides will advance. And I can't see the cursor anywhere, and I'm clicking. Okay. All right, now we're stuck. We tested this, folks, earlier. The arrow keys are not happy. They're not doing anything, and I don't see the cursor anywhere. Okay. Something worked. We'll keep going with that. Okay, so we had robots, right? And also people will relate to this as also the golden era, right? I mean, the Voyager missions and the Grand Tour, I think many of you will probably agree, one of the most successful science experiments in the last century in terms of our state of knowledge beforehand and our state of knowledge afterward about the outer solar system. And of course, followed up by more detailed studies of the Galilean satellites. And if this isn't something that some people might be too young to remember, they think about, of course, this selfie from Mars, the Perseverance rover. Oh no, I'm sorry, this is Curiosity, exploring Gale Crater now for almost 10 years. And so, we have these fantastic virtual exploration, our ability to follow these things through NASA and so on. And somewhat with a little less notoriety, perhaps, than these fantastic things, but nevertheless still important. A little shout out to UCLA here, which was the home for the Dawn mission. The Dawn mission exploring some of the small bodies of the solar system. In fact, interesting mission by the virtue of the fact that it's the only one that could go to a body, orbit it, study it, leave, and then go to another body and orbit it and study. And so Dawn first visited Vesta, differentiated asteroid you see here, and then Ceres, the largest asteroid, which got upgraded to the status of a dwarf planet because of its hydrostatic shape here, and a very interesting world with interesting possible astrobiological significance. And also in terms of the small bodies are comets. All right, so the ESA mission to Comet 67P and the Stardust mission, which visited Comet Wild 2. And these spectacular images of going around these very small bodies, seeing some of the emission profiles. And this continues today with the exploration in the asteroid belt from the Japanese mission to Ryugu and the American OSIRIS-REx mission to Bennu. Exploring these small worlds about what they have to tell us about the early solar system. And of course, the Voyagers are now venturing off into terra incognita. They're in interstellar space. The furthest machines that we've sent, Voyager 1 is, I looked this up last night, it's 14.5 billion miles from the Earth. And it, at its current speed of 37,000 miles per hour, it will reach the inner Oort cloud in about 300 years. So don't hold your breath, but we're on our way, right? On our way to the stars with this. And the upshot of all these missions is we have a very, good understanding now of, in fact, we've toured the solar system and we understand well the architecture of our solar system. We understand the four small rocky planets, the terrestrial planets in the inner solar system, the gas giant planets, the very volatile rich planets in the outer solar system. These are all shown, I think, according to approximate relative size. And then, of course, in the gap in between here, we have millions of asteroids and a dwarf planet, Ceres, here. And then in the region beyond Neptune, we have the Kuiper belt with, again, millions of small icy planetesimals habiting there. And you see some of them here, one of the largest ones, of course, being Pluto. So all of this has been, fantastic knowledge established by remote observation, by a series first, of course, of telescopes on the ground, in space, and then by, a flotilla, a couple of hundred actually, of machines that have been sent out there and doing, a flyby, or in some cases, orbiting and studying something in detail over some period of time. In other cases, landing on some of these objects, and in at least one case, landing with, and bringing 12 people, not all at the same time, 6 missions to the moon. And so this has been obviously fantastic, but there's other ways to think about this kind of exploration of the solar system that I think is not as well appreciated, except perhaps in the science community. So I'm talking about the general public, and that's what I really want to focus the rest of this talk on. And that is when we look at the samples of the solar system. And so there are other images that one could project, all right, instead of an image of a moon of Jupiter or something. Here's an exploration image from a basalt from the moon. And these are beautiful, instructive images in the same way that the others are. But these are images made in terrestrial laboratories. This is a thin section of a Mare basalt. Here's an image made by coloring X-rays of an inclusion, a xenolith essentially, in a carbonaceous chondrite meteorite. And this is, we're going to talk in a little bit more detail about this. This is one of the first rocks to have formed in our solar system. It's a refractory inclusion in the meteorite. And so we can learn a lot about studying these things in the laboratory. And that's what I want to focus on. In fact, here's now just a little montage a couple of images made in labs of other objects that you've already seen pictures of in this talk. So I started talking, seeing these remotely observed, but in fact, here's a piece of Vesta. Here's a piece of Mars. This is some of the material recently brought back to the Earth by the JAXA mission Hayabusa 2 of the asteroid Ryugu, and that's being studied very feverishly right now. And here is some cometary material from, and I'm sorry you can't see this down here, this is from Wild 2, the comet. Okay, so these are other kinds of images of solar system exploration. And I have a slide here that I borrowed from Don Brownlee. It's a little bit tongue-in-cheek because, of course, one needs remote observations, but this is the hand of Don Brownlee, and he has two black objects in there. And his point is that if you look remotely at many things, especially primitive fine-grained objects, they appear as just black rocks. And this particular one happens to be a 4.5 billion year old carbonaceous chondrite, and this is a piece of coal. And so his lesson is, right, sorry again for the cutoff here, but the key information is at the microscopic scale. And so to do that, you need a sample return so you can study these in the laboratory. And now I'd like to talk about Bob Walker. I'm really pleased to be giving a lecture like this in honor of the memory of Bob Walker. Bob was not only a great scientist, but a great mentor. And I don't know that he ever enunciated this in so many words, but when I look back at what Bob achieved and his scientific drive, I can see this real thread in there that drives toward this issue of analyzing the samples in the lab. And Bob's point was that solid samples remember aspects of their history. And the next point was I would put in the category of an intuitive kind of thing. And to get closer to the understanding the beginning or the origins of things, you need the most pristine samples. And for those of us in the physics department, that meant samples not messed up by too much geochemistry. All right, so you want to see through that as much as possible. And that meant in many cases that smaller samples often have a higher chance of, or a better prospect for preserving records of their origins. And as Brad alluded to, I bought into this because when I came here, we were studying these interplanetary dust particles, which we thought would come from comets. We had many reasons to think that, and it's still probably true, that most of them, especially the ones that look like this, are cometary particles. These are collected in Earth's stratosphere by high-flying aircraft. And you could bring them down to the lab and study their isotopic compositions, and that was a great thing. Bob also had the intuition that if you looked hard enough, interstellar dust itself might have been preserved in the most pristine samples that had not been affected by too much activity after that. And in fact, they've been found, and they were found at Washington University primarily, also with the University of Chicago. But really, these subspecies of pre-solar grains were identified here by analysis in the laboratory. And I'll talk a little bit about that in just a bit. And Bob also felt very strongly that innovative tools are required. Advances in laboratory science are required in order to understand and examine these samples at the correct spatial scale so that you could make inferences. And certainly that's something that he impressed upon me. And so he was very key in developing the ion microprobe or secondary ion mass spectrometry, SIMS, or so on. And this guy with too much hair there is in fact me, Bob and Glenn Crozas, professor of planetary science, also Bob's wife. And this is Scott Sanford, who went on to NASA Ames a very distinguished career as an infrared astronomer and sample return scientist. So this is something that I've bought into, and I'm still sticking samples, as Brad alluded to, into sophisticated laboratory instrumentation, some of it home built, some of it not, and using these ion probes to interrogate extraterrestrial samples. And I'm going to describe some of that work to you now. And in doing so, I wanted to just say that what I'm going to tell you is, well, a couple of things. One is that we, the royal we, the scientific community, know much more than we did in the previous picture. And this is a good thing. Otherwise, it would have wasted a lot of time in between that picture and this one with the guy who has less and more gray hair. And that the science is coming from all sorts of, it's an integrative activity. So this is coming from all sorts of different approaches to understanding our origins. It comes from astronomy, astrophysics, cosmochemistry, and the laboratory analysis of samples, as I said. And, one of the significant observations that have been made recently that we didn't know back in, at the time that that previous picture was taken is that, we now know, what is it, more than 4,000, about 4,000 planets outside of our solar system. So we understand a lot about planetary systems, but we still don't understand whether our system is particularly special or unusual or not. And that's something that we can certainly look forward to doing. But we do know that planet formation is a expected common occurrence of star formation. And the question that also was driving a lot of this, and it's something that I guess a lot of things you don't articulate until you try to put together a talk such as this, where you reflect on these things, is this question of, how special or common is a planet like the Earth? We don't know, right? What is required for this planet to be habitable? When, or said another way, more specifically, when and how did our life-bearing world arise? And here is one of the ways that I think the analysis of samples can really inform and complement the kinds of analyses that you get by remote exploration, because there are different kinds of questions that you can ask. Questions about chronology, for example, that you cannot do remotely. So that's a very long-winded introduction into what I'm going to give you sort of a vignette now of a few things that I hope to convey. And the first is to I'm going to talk about the solar nebula, so I want to make sure we're all on the same page, and introduce you to this concept. And the amazing fact, which still sometimes boggles my mind, is that we actually have samples from this epoch of solar system formation. This is not something that is necessarily obvious. And then after that, we'll talk about, these samples, which are derived from asteroids. And we'll see that there's a diversity of materials and processes. Again, talk about these first rocks of the solar system, and briefly, just the connections to our galactic inheritance that you can get by looking in detail at the microscopic scale of some of these samples. Very brief discussion of capturing cometary matter and what it is that we can learn from that, and also a little bit about the moon, and then finally finish up with just a couple of ideas and hopefully a discussion about the future of this kind of solar system exploration and how it fits into our broader goals. So as I sort of go through some of these, we're going to really just hit on a few high points, and I'm going to try to tell you some things, some conclusions that are the scientific community has a pretty good consensus about. But I don't have the time in a talk like this to really sort of justify or go into detail about how we know specific things. However, having said that, right, we're in the show me state. I welcome comments, discussion about, well, how do you know that? What, you've asserted this kind of thing. What is the reasoning for that? And that would be a fun discussion. So please keep that in mind. Also, if I should say, I like to do this in any talks. I mean, if I say something that doesn't make any sense because there's a vocabulary problem or whatever, and there's a very short question that you have, especially if this is more directed to the people in the room, that's just explanatory about something so that we can follow along, then please just interrupt and ask, all right? Otherwise, I don't know if we're connecting. Longer discussions we can have at the end, and that'll be fun. All right, so what do we know about processes of star and planet formation? We understand this pretty well because we have, a lot of astronomical observations and astrophysical ideas from cosmochemistry. So we have a pretty good idea. We know that planets are a typical outcome of star formation. And what we don't know, as I already mentioned, we don't know yet if specific planets like ours would fall in that category, but we'll get there. All right, so what we know is stars are formed in clumps or in large groups, let's say, out of clumpy materials that accumulate in the galaxy in what are called molecular clouds. These are extremely big objects, million solar masses. What you see obscuring the starlight here is because this is rich in dust, both rocky silicate dust and carbon-bearing dust, and also molecular ices, hence molecular cloud is the name, right? And this is a very cold environment. And this is where new stars form. At any one time, our galaxy has a few thousand of these giant molecular clouds, and they last for tens of millions of years. What blows them apart is, in fact, when they succeed in making massive stars, the massive stars will evaporate the cloud, essentially, and therefore it becomes a sort of self-limiting thing where the efficiency of star formation is something less than 1%, but it's still a lot, right? Because you start with maybe typically million solar masses. So significantly, somewhere in the galaxy, about 4.6 billion years ago, such a cloud existed. Maybe it was a little like the Orion Nebula is today. And here you see a picture of of objects in the Orion Nebula, which were at the time optimistically called protoplanetary disks. I think that's pretty good. That now sort of illuminated in silhouette against the sort of luminosity of the broader Orion Nebula. And 4.57 billion years ago, a fragment of one of these clouds that might have been 1 to maybe more, 1.5 solar masses, became unstable against gravitational collapse. And this happens all the time in the galaxy, but it's a very significant event for us because that is our solar system. All right, and what's important to realize is that this fragment is a mixture of gas and dust that are materials produced throughout the life of the galaxy in other stars. And so now they're coming together into this environment under the action of gravity, through the conservation of angular momentum. You're collapsing from enormous distances, and so this thing is going to spin up into a disk, all right? And as matter accretes to the center of the disk, some of the high angular momentum material is ejected along the axis of rotation in these bipolar outflows. And these are real pictures here where you can see this is going on today. Here we're looking at the disk edge on, here somewhat obliquely. And the point is also that in the early stages of this collapse, there's a lot of energy released, and the situation is fairly violent, and things get mixed up, get heated up and mixed up. And this is now an artist's conception of what our disk may have looked like 4.5 billion years ago. This is, you have to imagine, right, that in this disk of gas, which you can't see too much, and the dust going around in here, that our solar system is what? It's like a little less than 1/3 of the age of the galaxy. So So this stuff has been produced by many, many, many generations of stars prior to coming together in our neck of the woods, so to speak. And in here, you have lots of high energy events. These things are colliding, they're mixing, they're evaporating. It's hot in the center and cool toward the periphery of this. And this is, to first approximation, a great homogenizing process, right? And so this is our field area where we're trying to understand the origins of the planets. And fortunately, and this is kind of the amazing part, some of, and I hope this will run, yep. We get materials delivered from the solar system. Some of them come for free. And here's a dash cam in Siberia, essentially, in northern Russia, early in, well, not so early in the morning. It's still dark. It's 9 o'clock, and this guy's on his way to work. And this happens across the sky. These people, this is very interesting to me. They just keep walking along. Nobody looks up. And our driver just, the light changes. You can't quite see that. And then he drives off. But anyway, that's another subject, I suppose. And the point is, the Earth is still accreting material. About 100 tons a day, maybe a little bit more. This is the Chelyabinsk meteor, right? It gave the meteorite. It exploded in the sky up pretty high, which was good because it released about 400 kilotons energy of TNT. And fortunately, that was pretty high up. So there were a number of injuries, but nobody was killed. But from our point of view, it's interesting because we get these extraterrestrial materials. So the meteorites arrive to the Earth. We have a lot of them. We got 65,000, give or take, what I like to say, in captivity. And the vast majority are derived from asteroids. So how do we know that? Well, we have these videos. Now everything's videoed in the world, right? I mean, we're probably being, well, we are being videoed now, aren't we? There you go, at least I am. And so we know that these meteorites are coming from asteroids because in the few dozen cases now where we've been able to recover a meteorite, you have its trajectory, you plot it back, and its aphelion is in the asteroid belt between Mars and Jupiter. And there are other reasons to expect that. So we know the vast majority of meteorites are from asteroids. A number of years ago, I stopped counting, but we have meteorites also from the moon and from Mars. Probably none from comets. There are not so many compared to 65,000, right? But we still have a lot of them. And so the point is, by studying asteroids, by studying meteorites, we can learn about the nature of asteroids in some detail. And we also have flown by asteroids, and so we can see them, and we can probe them with radar. And here are some asteroids, typical asteroids. And you can see they are very irregular objects shaped by collision, not in gravitational equilibrium shape or hydrostatic equilibrium. There are millions of them. Where do they come from? There are millions of them between Mars and Jupiter. Well, we have samples of them. So we can address the question about the origin. Are they, for example, collisional debris? Was there a planet there that got broken up? It's one possibility, right? Or are they something else? Are they bits of the solar nebula that never got into a planet? And that, in fact, turns out to be the answer. How do we know that? Well, here is a polished slab of one of these meteorites, and it turns out the vast majority of the meteorites that are observed to fall are like this. They're called chondrites. And what you see, the sort of brighter bits here are metal that is reflected. This is just a light image, reflective image, and you see darker material in here. This is silicate rock. And so objects like this are an intimate mixture of metal and rock. And what that means is that this object was never melted. Why? Because if it was melted, what would happen? You would have two melts which would separate from each other, a metallic melt and a rock melt. If it was in a gravitational field, the metallic melt being much denser would sink, and you would be separating the metal from the rock. And that doesn't happen, right? This has the same metal to rock ratio as the sun would have. So the same magnesium to iron ratio, for example. And that means that this is like a cosmic sediment. And that is extraordinary because the asteroids, right? This is the sort of amazing thing. It's pretty much thanks to Jupiter, right? Disrupting things and not allowing a giant planet to form in this region. So here's again an artist's conception. We're now inside the solar nebula. We have these kinds of objects, which are the asteroids, and they've been around since the beginning. And from time to time, we have collisions which send us meteorites. And here is the thumb of Andy Davis from the University of Chicago with the Murchison meteorite. And all these little bits in here were bits of material that were in this nebula. So it's not just that we can study the nature of asteroids. The amazing thing is we have samples that you can hold in your hand from the time that the solar system looked like this, right? And so from that early epoch, and that's what you can then study. And these things have been in cold storage because asteroids, so meteorites are relics from the solar nebula. And you know, most of them are these chemically undifferentiated cosmic sediments. Yes, there are some that have been melted, that were on asteroids that melted, and we can well recognize these because we have, you know, we can compare them to igneous rocks on the Earth. So for example, we recognize some of these things that are basaltic, and this is a eucrite's probably a sample of Vesta. We have samples that we think come from Mars. And of course, anybody who's visited a museum sees the very overrepresented iron meteorites, which are the cores of asteroids that are no longer, that were in fact disrupted by collisions and so on. And a key point in all of this is to realize asteroids are small. So the label's gone off here. This is Ceres. Ceres has half the mass of the asteroid belt. And so, you know, compared to our moon, there's not much stuff there, right? All right, that's fine. But what's important about that? Well, they're small. And so they have a large surface area to volume ratio, so they can't retain geologic heat for very long. And yes, geology happens on these asteroids. Here's Vesta now compared to many of the other ones that I've shown you already. And there's one under here that you can't even see. And that one is this one, which was explored by the Japanese Hayabusa 1 mission. This is, you can see, this is probably not much bigger than the campus. Maybe even smaller, I don't know. This is a near-Earth asteroid called Itokawa, and we have samples brought back from that, and we know it's an ordinary chondrite. So this is what this thing looks like, essentially. This is an ordinary chondrite, cut and slabbed and polished, and you see all these bits in here. Well, these things are what are called chondrules. These are melt droplets. So this was formed by some processes in the solar nebula as individual objects pulled into spheres when they froze by surface tension. But then they come down as a sediment on an asteroid and are not then again melted. All right, so the chondrules and basically almost everything you see in this picture was formed as free-floating objects in the solar nebula. Here's another slab of another kind of meteorite, also a chondrite, a cosmic sediment. This is a famous meteorite called Allende, which is a carbonaceous chondrite. So as usual, everything gets a name and a classification. And the reason I wanted to show you this slide is the point is that, yeah, all of these things were formed in the solar nebula and then accreted as a sediment on some asteroid. We don't know which one, but all of the things in here could not have been formed at the same time in the same place by the same processes in the nebula. Why? Because they contain things like the chondrules, which were melted at 2,000 degrees, the CAIs, calcium aluminum rich inclusions, which I'm going to talk about in just a second, and other material like organic matter, water, and even pre-solar grains, which could never have seen those high temperatures or they would be destroyed. So this tells us that there's a wide diversity of materials, I'm going to talk about the CAIs, that formed at different places and different times in this nebula. And an important question that is the subject of much research is how did and when did these things come together? They're in an asteroid now, but what were the processes that were involved in that? Let me talk just a minute about calcium aluminum rich inclusions, because they're fascinating. At least I find them fascinating because they're the first rocks that we know formed in the solar system. And in some meteorites, like this CV chondrite and Allende-like meteorite, although this is a desert one, found in the desert, you don't need to be an expert to find these, okay? You slice this open, you see this big white object in here, and you can see that something is very different. And that's one of these CAIs. Now, in other meteorites, you do have to have certainly specialized tools to find them because they're much smaller. But what are they? Here's Allende again. Here's another one of these CAIs. They are refractory inclusions. So they're basically high temperature minerals, oxides of calcium and aluminum, and some silicates as well. Facite is a calcium titanium bearing clinopyroxene. For those of you, it's not an official mineral name, but you see oxides of calcium and aluminum here and so on, objects that would form at very, very high temperatures. And they show different physical formation mechanisms. Some are condensates. So these kind of images here, the calcium, this is an X-ray image made of a polished slab of a meteorite, and the calcium X-rays are colored green, and the aluminum are blue, and the magnesium X-rays are red. So the calcium aluminum rich inclusions you can easily see stick out as this sort of blue-green thing, and there's some other minerals in here which are purple, which are the spinels, and so on. But this is a convenient way of looking at these things and starting to examine their mineralogy in detail. Some of them are condensates, some were recrystallized, some were clearly melted. Here's a nice big circular one. This is not colored, but here's a colored version of a similar one, and so on. This is a small one. So there are these high temperature events that are occurring, forming these igneous rocks in many cases. And what's fascinating about them is that, for example, it's an igneous rock, it's a refractory, uranium is a refractory element, lead is a volatile element, so you can get a very good precise date by uranium-lead dating of these. And this is in fact how we date the beginning of the solar system. So this is only possible because we have samples, right? And these things formed 4,567 and change million years ago, with an uncertainty of about a fraction of a million years, maybe let's call it about a million years. And so that's time zero. And they're also interesting for a number of other properties that they have, including the fact that they have anomalous compositions of different isotope compositions. And I'll talk a little bit more about some of this tomorrow when I talk about oxygen isotopes in the solar system. But for today, I want to talk just briefly about extinct radioactive isotopes, because they're also present in these objects. And that is important because once we have radioactivity involved, now we have the chance to have a clock, right? So we can do chronology. And that is also something you need to have the samples to put into a mass spectrometer. So you can ask the question, okay, they're old, 4.567 billion years. How do you know there's not something even older? How do you know they're the first rocks, all right? So how do you know they formed at the beginning? Well, These are calcium aluminum rich inclusions. And it turns out that when the solar system formed, when this solar nebula came together, in the molecular cloud, there were radioactive elements that were there, just as there are radioactive elements on the Earth now, right? And some of these, you know, the long-lived ones, but there are also ones with shorter half-lives. And one of them was aluminum-26, which is the most important short-lived, now extinct radioisotope. And of course, this is an aluminum-rich object. So aluminum-26 beta decays to magnesium-26. This is my only graph that we have to worry about tonight, all right? This is a discovery slide made at Caltech a long time ago now. This has been done many, many times since then. And what you see is that if you take apart one of these CAIs here, and you take apart the different mineral fractions, those mineral fractions, this is a plot of the magnesium isotope composition of 26/24 against the aluminum to magnesium. So some minerals like aluminum a lot, and others, like the pyroxene, has a lot of magnesium. So you have a low aluminum magnesium ratio. And if you look at this, they form a line. And this line says that there's, you know, those minerals which had more aluminum have more magnesium 26. Whereas everything else, if we go out to the garden here and pick up some rocks, its magnesium 26-24 ratio is on this dotted line, right? So something is elevating the magnesium 26 here, and that is because aluminum 26 used to be in this rock when it formed. And over time, it decayed to magnesium 26, right? And so this, how much you can calibrate this, and you can determine that about 50 parts in a million of the aluminum were this radioactive type compared to the run-of-the-mill aluminum 27, which is stable. Okay, so what? So what does that mean? So you had aluminum 26 was incorporated live into this rock when it formed. Big deal. What does that mean? What I haven't told you is that the half-life of aluminum 26 is less than 1 million years. It's about 3/4 of a million years. So what does that mean? Well, the aluminum 26 had to come from somewhere. Where did it come from? Where do all the elements come from? Well, they're made in stars. Aluminum 26 comes from massive stars, and maybe from the winds of massive stars. We could have a long discussion about that. But the real question is, okay, you make some aluminum 26 in a star somewhere. How long could it have taken to get into a rock in the solar system? Well, what do we know about radioactive decay, right? After one half-life, you have half of the parent left. After 2, you have 1/4. After 3, 1/8, and so on. The upshot is, if you wait, this is half-lives, and this is the proportion left. If you wait, I don't know, 5 or 6 half-lives, it's gone, right? It's decayed away into magnesium. So it wouldn't be in the rock. So this means that effectively you have, let's say, 5 half-lives, maybe 6, not more than a couple million years, as it turns out. So this is a direct connection to the pre-solar environment that formed the solar system. It also can provide a means for a chronometer, but that's a complicated story. It depends on some assumptions. So that's one connection. What's another one? All right, so what else can you learn from looking at these samples? Well, here's a cartoon that I borrowed from Larry Nittler, also from WashU. You should invite him sometime to do one of these. It would be very good. And this is about the pre-solar grains. And the idea is that you have materials contributing to this molecular cloud from different kinds of stars. They get into the solar system in an asteroid, and that comes to us as a meteorite. If you then can take it apart, and they do this rather thoroughly, let's say, this is called burning down the haystack to find the needle. You destroy most of the locally made material, and you can find some materials, some grains that survive various chemical treatments. And in fact, in this way, small materials which survived this, what I call the great homogenizing event, the great cosmic blender that was the solar nebula, that survived that somehow, right, can remember their origins in different stars. And these are the pre-solar grains. I lied. This is the second plot. Sorry, I forgot about this. But this is a simple plot in a way, because each dot you see on here is a pre-solar grain measured here at WashU. And there are thousands of them. And the point is, this is the nitrogen isotope ratio. This is the carbon isotope ratio. And everything not only in this moon and on this planet, but in the solar system would be somewhere around where this bullseye is. And you see that these kinds of grains that are colored in different symbols because they have different kinds of groupings come from, have very different isotope compositions. Why is that? Well, they were in a nuclear reactor. They were made in the outflows of stars which were losing mass at the end of their life, one way or another, and they condensed from that gas. And this is some of these are stellar condensates from other stars, little rocks that formed in other stars, and you can put them in electron microscopes and you can image them. So each of these is a rock, a dust grain, but in many cases polymineralic. So it's a rock. They're tiny. This is a 1 micrometer scale bar or even smaller. And they consist of oxides and graphitic material and silicon carbide. And all of these rocks were made in stars other than our own solar system. And so we can connect somewhat to our galactic origins by looking at these kinds of materials. Okay, I'm going to move on a little bit to show you, again, this is just another example of the kinds of materials that we can look at and we'd like to get more. And this has to do with, the stuff I've been talking about is formed. This is an artist's conception of this solar nebula disk. Of course, it's hot in the center where material is accreting to form the protostar. And it's very cold temperatures out here. And the significant sort of temperature demarcation that's illustrated sort of schematically here is the frost line or the snow line. Because outside of here, water, right, will be so cold it will condense as a solid, so it's ice. Inside of here, it's a vapor, and there's a lot of water, right? Water is the most abundant triatomic molecule in the galaxy, and it's very important. So when it condenses out here, then you can grow things big, but that's another whole story. So all of these ices can form out there. And why is that interesting? Because we have, again, like the asteroids are planetesimals of rocks that were primitive and not melted in most cases. In the outer solar system, we have examples of planetesimals which are icy rich, which we don't see most of the time until they come into the inner solar system and heat up. And then, of course, they release their ices, the sublime, and the dust comes out, and you get these spectacular displays, and they're known as comets. And we have collected some comet dust. This is a discovery mission led again by Don Brownlee, which is called the Stardust mission. Maybe optimistically, its goal was to collect stardust. It didn't do a lot of that, as it turns out, but it did collect comet dust. And the idea is you fly through the tail of a comet and expose a collector, this kind of fly swatter looking thing. The little tails on the cometary dust, this is an artist's license, so you can see them. Of course, there's no ablation going on there because there's no atmosphere. But nevertheless, they come and, at this case, 6 kilometers per second. This material that was used to collect it is a very low density glass called aerogel. And so it has the ability to slow this little microscopic bullet, if you will, from 6 kilometers per second, which is 6 times the speed of a rifle bullet, to 0 in a short distance, and capture it intact in this low density silica gel kind of material. And skipping ahead, this was brought back to the Earth. And I have to say, I was there when it was opened, and at first it was opened, it looked like the day they sent it off, and everybody was worried. Maybe it didn't open. But then, people were looking and so on, and sure enough, you could see some big splotches of cometary material that had hit into this. And one of the other key points to emphasize in terms of, so you're collecting these microscopic bits of comet dust, but you've brought them back to the Earth, right? So you can do anything you want to them that you can get funded for. And you are not limited by mass, power, or time, right? If the experiment doesn't work today, maybe it'll work next week, right? And you keep at it. And so that is important and so you can have instruments like the nanosims here, transmission electron microscopes, or instruments like a synchrotron, which is the size of a shopping center or more, to analyze these tiny things. And when you do that, you basically have two views, I like this, of comet field 2. You have the nucleus in here that you cannot see, but then you can see this is now a 200 nanometer scale bar, a mixture of olivine and pyroxene and some melt products in between. And of course, one can analyze these, and surprisingly, one of the first particles found was in fact a particle rich in the kinds of minerals like perovskite, like spinel, some aluminum dioxide, things that look like these CAIs, hot minerals in the coldest place in the solar system. This was an unexpected surprise, a thing by most people. There were one or two people who kind of thought we might find some things like this. And the question is, how do you do that? Where does this come from, right? It implies that there have to be mixing processes of making things in the hot regions. This is now a logarithmic scale. This is where asteroids are at a few astronomical units. The comets, right, they have all these ices in them that condensed at very low temperatures, I don't know, tens of Kelvin. And so, but mixed in that, you have materials which formed at thousands of degrees C, or 1 to 2,000. So how does that happen? Well, you have to have radial mixing, either turbulent mixing along the disk, or maybe throw things out above the disk and have them fall in. And so this is the kind of things that you can learn by looking at the microscopic details. Let's see, we got a little bit more time. Can I talk about the moon, Brad? Sure. Briefly, I thought Brad might think that that's not a bad thing. Okay, so just briefly, again, to make the point about why samples are so important. Like this picture, this is a picture actually taken by Galileo, looking over its shoulder, so to speak, on its way out to Jupiter. The moon is in the foreground here, and it's moving left to right on your screen. But I like it because it emphasizes, our close connection here between this planet and our satellite. And the moon and the Earth have been together for most of the history of the solar system. And what do we know about this? Well, we've gone to the moon. It's certainly the object besides the Earth in the solar system that we know the most about. And in fact, it's because we were there, right? And so here's a picture of Jack Schmitt, Apollo 17, the only scientist to go to the moon, in fact. And the Apollo missions have brought back several hundred kilograms of rock and soil. This is complemented by a smaller amount, but collected over a wider area, again, from the 1970s of the Soviet missions of a few hundred grams of material. And then just last year, China. China is now a significant player in the game, have returned very interesting samples, which are much younger than the other samples on the moon, and about 1.7 kilograms of these materials. So we know a lot about the moon. What we know from the geochemistry of the rocks on the moon and in comparison to the Earth, it tells a fantastic story that I think we would not have another way to really come up with. And this is the giant impact origin of the moon. This is, the mother of all environmental disasters on the Earth. So This is a really incredible thing, but this is basically our best idea for explaining the geochemistry of the moon rocks. And so that's a very important fact. The other thing is that we know about the moon is that it's been heavily impacted, right? You have craters, you've got these basins all over the near side. This is a little bit controversial. I told you when I would tell you about things that everyone agrees on. Well, this is a little bit more controversial about the impact ages of these basins and so on. But nevertheless, they're old, right? And they might be sort of clumped in time, just under 4 billion years, depending on how you squint at the data and so on. And the point is that one of the things we know is that impacts this is a schematic, right? This is time running to the right as it should. So this is, back at the beginning, this is now. And we know that the impact rate was very high at the beginning as things were getting cleaned up. And the idea that these basins might clump gives rise to this idea of a potential lunar cataclysm or increase in the impact rate at around 4 billion years or a little bit less than that, which gets termed this late heavy bombardment. Late heavy bombardment, but late compared to the beginning. And this has been an idea that's been around for a long time. It needs to be tested further. But the important point, and the thing that's key about this is it's obvious that what happened on the moon happened on the Earth. And so you could say, well, what was going on at the Earth? Well, we know life is originating somewhere in this epoch. Here's the oldest fossils. We have some chemical evidence for life at this point, maybe even earlier. We don't know. But clearly, this is a very interesting and important point of time in our planet's history. And so the moon is the place to go to learn about the early Earth. This is our best recorder because we've been together for those 4.5 billion years. So these are some of the samples I've talked about. I hope you've gotten some sense of the kinds of things, the kinds of questions that can be uniquely addressed by looking at samples. Could have picked many other ones. These are just a few, vignettes that I decided to talk about today. The samples that are available, it's always important to remember, Earth is our favorite planet, and we have the most of it. So we can learn some things about the Earth. I've talked about the moon, not so much about Mars, but meteorites, mostly randomly selected asteroids. We don't know where they come from, any individual meteorite, which is a limitation. But now we're starting to go out and collect asteroid materials, and so we can learn more about that. So here are some of these missions. Comets, so the Stardust mission was the first pass at this. It should be done collect cometary material in a less violent way than trying to slow it down from 6 kilometers per second. So we need a lower encounter velocity, preferably a lander. I'll talk tomorrow a little bit about the Genesis mission. I've shown you a little bit about extrasolar material we have, so the pre-solar grains. Of course, we also have the cosmic radiation. And one of the important points to remember in all of this is that one of the samples we don't have are ices. And we don't really know about the organic matter that we have, about how representative it is or how much things that might have been changed there. So sort of coming back to the beginning, as I said, I hope that you got a sense of how at least the analysis of samples is an important part, maybe even a key part, to unraveling processes and timescales to address this question of how did we get here? The next big question, of course, the ultimate question is, are we alone? And I think in the future, this is something that, again, sample science will, in concert with astronomy, but now also in concert with biology, will help us address. And I think it's a particularly exciting thing because, formerly this kind of a question, are we alone? This was left to the realm of philosophers and religions and so on, which is fine. But now I think it's also in principle addressable by scientific methods. And it's something that we can really hope to have an answer to scientifically. The As of earlier this year, there were 165 active or planned solar system missions. So my message to the young people here or online is that, you know, the golden age of space exploration and exploration of our solar system continues, all right? Just because we haven't been outside of Earth orbit in 50 years doesn't mean it's only ancient history as people, right? We have our representatives out there, the robots that are doing a great job, and we're going to return as people again, hopefully not too far into the future. And so all the tools are employed in all of this, right? Telescopes, spacecraft, samples brought back by robots and by human explorers, and that will certainly include women next time, all right? And the big issue, of course, is the issue of life, and the place to look first is Mars, and there are plans to do that. Then I think the next important key point is to go back to the moon and study it like a geologic object, like it deserves, and there are plans also to do that. And one can also imagine going to the outer solar system and trying to answer this question by addressing things that were also potentially abodes for microscopic life, right? Such as geysers on Enceladus or oceans on Europa and so on. And so with that, I'm going to close and thank you for your attention, and happy to have any discussion or questions that arise. Thanks very much.
Oh, I thought you had the first question too. Questions?
If there are any online too.
I'm looking online. Questions online, please. Chat. Hey, either one of those works. Bill was going to ask.
It's not so much a question, but a comment. One of those things that struck me on one of the graphs you did show, Typhoon Lee's old plot, that number 5 times 10 to the minus 5 has held up incredibly well.
Yep, it's true.
I mean, what?
It's now 5.23
All right.
times 10 to the minus. No, there's
Is
discussion.
that completely luck, or is this? I mean,
How did they get it right? So you know, sometimes you wonder, right? You know, no, there was a lot of skill involved, but the method, you know, one of the other things that I haven't emphasized really is how the experimental methods have improved enormously, and how when you have samples, right? So, you know, I'm working on samples brought back from the moon by Apollo astronauts, and we're asking questions that they didn't, not just they, but the scientific community at the time didn't anticipate would really be addressable perhaps, or hadn't just really thought of, because this is the way, one of the strengths of samples is it allows the scientific process to proceed in its natural way, where you have, you know, ideas and you test them, and then that leads to another ideas and so on. And you have generations of scientists who can get involved in that and can learn. And as the experimental methods improve, then you can address completely new questions. So the story about aluminum 26 at its fundamental level, and it's not just aluminum 26, there are now a couple dozen of these short-lived radioactivities, shows we have a very close connection with the interstellar medium that produced our solar system. And the next question is much harder to address, is now you have a clock which is running fast. So in principle, you can use that as a high resolution timekeeper, but that relies on assumptions that at one time it was homogeneous everywhere. And that's harder to address and somewhat circular sometimes. But yeah, no, things have, you know, things have been tested. That particular number has been tested hundreds of times, including by me.
So this is not your area exactly, but you've mentioned organics a couple of times. And clearly there's a lack of data that, but so this question has to do with the status and the prospects for looking at the chirality mix of molecules with chiral centers.
Right.
And maybe there's, I don't know what data there is now, but what is the status and what is the future prospects for getting that mix?
Well, this is a extremely well-recognized and important question. Thank you for bringing that up. I didn't talk in detail about organics because I'm not an organic chemist, and having said that, I can mention that for example, in that Murchison meteorite that I've shown you, right? You find amino acids, you find sugars, you find all sorts of interesting organic. You find a macromolecular complex tar-like organic, which is insoluble in most acids and so on. And so it has connections to the pre-solar molecular cloud. All right. Now that doesn't mean it hasn't been that it exists unmodified from there. And certainly the organic materials, although there's relatively little geologic activity on most of the asteroids, that's not completely true. And I said, there's a whole range. And certainly organic synthesis has happened, or modifications have happened in asteroids with the assistance of fluids. And with regard specifically to the chirality issue, this has also been investigated, and these are, I think, pretty well mixed. So it's a racemic mixture of these, but I don't know the number. I can't remember. The person who was most heavily involved with that was Sandra Pizzarello at Arizona State, who unfortunately died last month. She was quite elderly. But if you want to follow up on any of in the literature, you can Google Arizona State, Sandra Pizzarello, and you see some of her work on this. She was one of the first ones to really address that over a series of, maybe a couple decades. And that's certainly something that one would want to look at first, right? So for those who don't know, these organic molecules have a handedness that has, at least on this planet, been selected by living things in a certain way. And so it gets to the issue of, if you find organic matter, how do you know that that means life, right? This is not, it's carbon and hydrogen are abundant things that will react in many ways and make complex molecules. Doesn't necessarily mean that, I don't know how you want to define life, but it's not necessarily replication over time in the way that we would think of it. But certainly there would be signatures like such things like this that are not so far out of equilibrium, right, that you would indicate that that's probably a biological process. And that's certainly something one would want to look at very carefully in any return samples.
But there's also a clock there, because the racemization, if it involves hydrogen, is not infinite. So
yes, right. So that clock, if I understand correctly, is mostly involved in the degradation of formerly living organic matter, and then how it degrades back into a more disordered state, right? And so that is a possibility too, right? That, for example, I don't really know what's being done with Mars. So if we dig, all right, there's not much on the surface. If you dig on Mars and you find organic matter, that's one of the things you would want to look at. But then you would have to say, okay, well, stuff happens on Mars, right? I mean, how do you know it wasn't living billions of years ago, and then over the time it's been degraded to the point where you have a hard time recognizing that. So Mars sample return, I didn't really emphasize too much on this, but this is going to be an exciting but complicated task, right? And complicated in the sense that we know life arose on this planet. And if you go back 3.7, 3.8 billion years ago, it's hard to figure out if what you're looking at there is really signature of life or not, right? So things happen to the samples.
I have a question from online.
Yep.
And this is one, you could take a half an hour to answer this,
I
but
try
maybe
not to,
quick,
sorry.
no,
I tend to do that.
a quick answer would be, how different are the materials brought back from spacecraft from other objects from what we have right here on Earth?
It's a great question. And this is something that is really being worked on right now because the Japanese space agency, JAXA, and people there have brought back a sample from a very dark carbon-rich asteroid. And it looks like a CI chondrite, which are the most primitive chemically meteorites. And they're trying to figure out exactly, is it that or is it slightly different? And if it is, it appears to be slightly different in certain ways. And I can't say I know a little bit more than I'm allowed to say, but mostly not. Meaning mostly I don't know all the details. But one of the things is that most of the meteorites we have on Earth, so for example, in particular, the meteorite on which we base solar abundances fell in a field in France in 1856 or something, and then was stored in a wooden drawer in a museum in Paris for the last 170 years. And so you can imagine, well, maybe not all that time. Now it's stored more safely, but you can imagine it's not the same as it was before it came to the Earth. All right. And so it's an interesting question if we go out and we get these things and now we know how to preserve them much better. We can see how well they compare. And every meteorite had to survive passage through the Earth's atmosphere, which is a non-trivial process. Right? Many of them are found on the ground somewhere. So that's an issue too.
Another good question from online. For the samples that are collected by missions, how is the selection prioritized? And as an example for the moon, how is that sample collection prioritized?
You mean once it gets back to the Earth, like do you get some
no,
and I get
no,
some?
if you're on the moon and you're collecting samples, how do you know which ones to bring back?
Ooh, that is, you ask really smart guys like this one who studied the moon a lot. So you have a plan, right? And then you try to execute the plan, but maybe something comes that's surprising. And so maybe you find an orange glass and you decide, I better pick some of that up and bring it back because, and something like that. So yeah, again, one of the things that's interesting about sample science, and well, this is true of all of these exploration missions. You go with an idea, right? Because you have to build instruments to make a measurement, or you have to decide that you're going to collect a certain sample, and you hope you get the right thing, but you may not. You may be surprised, and you may find that you want to get something else. And this is one of the interesting things about eventually sending people, right? Because these decisions can be made in real time. Whereas if you have to program an instrument to do something millions of miles away, well, you have to think about ahead of time all kinds of contingencies, and maybe you didn't think of everything.
Now, this is playing out right now on Mars with
Sure.
scientists on Earth trying to figure out which are the right samples to collect, to cache, to
Exactly.
eventually bring back to Earth. And it's
Right.
not easy. A lot of scientists in a room arguing. 30 scientists, 30 different ideas.
And with different interests,
Yes, right.
right? So you do the best you can.
So any other questions here? I have a question. This is an easy one to answer. Hopefully it's an easy one. On your last slide, the next to last slide, you put up 3 different objects, 3 different sample return kind of ideas, concepts, places. if you could design the mission yourself, where would you like to get a sample from? You can only have one, one object or maybe.
Personally or as a community?
Personally.
Well, I mean, and I ask that because I would really like to have a comet nucleus sample return. All right, but I'm 63 years old. And to go to the outer solar system and back takes a long time. So you need to be somebody who's maybe 20 or 25 years younger than I am to do it. And that would be a great thing, I think. Otherwise, personally, because of, awareness of time and awareness of the importance of problems, I would like us to see us go back to the moon and study it as a geologic body the way it deserves to be studied. Whereas, the previous samples that we have from the moon were taken samples largely of convenience, not completely, not the later missions, but all from the equatorial near side of the moon. And one needs to go to the polar regions of the moon, and one needs to date the big hole at the south pole of the moon, and do the proper geology that has been waiting for now many years to be done. So that's something I would like to do. And the reason if Mars is your favorite place, I have nothing against Mars, but I'm not a biologist, right? So I personally would not be working on the most important question of Martian samples. I would have to defer to others. And so you asked a personal question, I gave you a personal answer.
Oh, thank you. If there are no other questions, I'd like to echo one of the comments from online. The comment is, awesome presentation. And I totally agree. And I hope you will agree that we've had a great presentation here from Professor McKeegan. And let's get out there and explore.
Absolutely.
Get more samples. Thank you.
Absolutely. Thank you. Son, what did he say? Oh, that was his question. How do they choose?
Yeah. That was great.
Good.
Thank you,
Well, at
Danny.
least I know he watched. Okay. Okay.
I like that question. So, yeah.
Okay, so I think this is Jan's.
Okay, I can get that back to her. And